This is Linear Algebra, Lecture 3. And we started matrices yesterday. And we're going to spend today talking about matrices. So let me emphasize the following, because the text for this course are the chapters uploaded to Blackboard. So there's chapter 1 on linear equations, and there is chapter 2 on matrices, and all the homework assigned is in these chapters. I had also uploaded a textbook on linear algebra that was available free. That's there simply as supplementary reading. If you want to read it, you can read it. There are many, many books and lectures on linear algebra on the internet that you can download or view for free. But that's not the text. That's simply there if you want to look at it. But the text are the chapters that I upload, and there'll be 4 or 5 or 6 of them in the course of the summer semester. And now we're starting chapter 2 on matrices. An M by N, this is read as M by N, matrix is a rectangular array of scalars, numbers, real, complex, whatever scalars you're looking at, with M rows and N columns. So for example, if I look at the matrix 1, 2, 3, 4, 5, 6, this has 2 rows. Here they are. 3 columns. 1, 2, 3. So this is a 2 by 3 matrix. In general, the matrix A, B, C, D is a 2 by 2 matrix. And so on. And there is a certain algebra of matrices, which is very simple with respect to addition and scalar multiplication. So suppose we let capital M, lowercase mn of R, be the set of all M by N matrices, where the coordinates, the numbers in the matrix are real. So M is the number of rows, N is the number of columns, R is the scalars.
Yeah.
And we can add matrices of the same shape. You can't add matrices that have different numbers of rows and columns. But if you have, for example, let's look at an example, 1, 2, 3, 4, 5, 6. This is a 2 by 3 matrix. And I take, I don't know, 7, 8, 9, 10, 11, 12. It's another 2 by 3 matrix. You can add them, and you add them by just adding coordinate-wise. So the number in the first row, first column, here is a 1, here is a 7. You add them, you get an 8. 2 plus 8 is 10. 3 plus 9 is 12. 4 plus 10 is 14. 5 plus 11 is 16. 6 plus 12 is 18. So this is the sum of the 2 matrices. And our standard notation, if you have a matrix A, we might write it as simply Aij, by which we mean the matrix. This is going to be an M by N matrix. you write the elements in the first row, A11, A12, up to A1n. The elements in the second row, A21, A22, up to A2n. If you have the ith row, AI1, AI2, up to AIN, down to the last row, AM1, AM2, up to AMN. So this is the ith row. What would be the jth column? Well, this would be in the first row, the jth column entry would be A1j. This would be A2j. This would be AMJ. The element in the ith row and jth column is Aij. So the standard notation, Aij is the coordinate of A in row I, column J. So when you see a matrix with entries and each coordinate has a double subscript I and J, I is telling you the number of the row and J is telling you the number of the column. That's pretty easy. That's how you add matrices. And you can also multiply them by a scalar. So if you have the matrix 1, 2, 3, 4, 5, 6, you multiply it by 7, you multiply each coordinate by the scalar. 7, 14, 21, 28, 35, 42. And with vector addition as matrix addition and scalar multiplication, the set capital M sub Mn of R is a vector space. The vector space simply means you can add the elements. You can multiply the elements are matrices. You can multiply by a scalar, and all the usual properties of addition and scalar multiplication that hold for vectors in Rn also hold for vectors or for matrices. You cannot add, and this is important, cannot add matrices of different sizes, different shapes. So if you have 1, 2, 3, 4, 5, 6, and you wanted to add this to 7, 8, 9, 10, 11, 12, this is a 2 by 3 matrix, 2 rows, 3 columns. This is a 3 by 2 matrix, 3 rows, 2 columns. Impossible. Or at least I should say, not defined. So we do addition of matrices only for matrices of the same number of rows and columns, the same shape or the same size. Okay. Now, what about multiplying matrices? So matrix multiplication is extremely important, but the definition is a little bit more complicated. I should say just one other thing. Suppose we have the matrix A, say it's 1, 2, 3, 4, 5, 6. There's an operation called the transpose of a matrix. So the transpose of A is a different matrix. I'll write it as A with a superscript little t for transpose, obtained by interchanging the rows and columns of A. So what does that mean? Here's the matrix A. In A transpose, the first row of A, 1, 2, 3, becomes the first column of its transpose. The second row of A, 4, 5, 6, becomes the second column of the transpose. And you'll notice, for example, that the first column of A has become the first row of A transpose. The second column of A has become the second row of A transpose. The third column of A has become the third row of A transpose. So interchanging the rows into columns gives you the same matrix as changing the columns into the rows, and what you get is called the transpose. And we say that also, if you have an m by n matrix, it's a square matrix if it's a square, if the number of rows equals the number of columns, and it's a rectangular matrix in general. But if the number of rows equals the number of columns, m equals n, the matrix is called square. And a square matrix is symmetric if A transpose equals A. So for example, the matrix 1, 2, 3, 4, 5, 5, 6, this is symmetric because if I take the first row, it is the first column. If I take the second row, it is the second column. If I take the third row, it is the third column. So a matrix is symmetric if it's equal to its transpose. Another way of saying that is, if you look at if you go down the diagonal of the square matrix from the upper left-hand corner to the lower right-hand corner, that's called the main diagonal. If you reflect the matrix through the main diagonal, you get exactly the same matrix. 2, 2, 3, 3, 5, 5. So symmetric matrices turn out to be very important later on. Matrix multiplication. So that's a little bit tricky. Because you cannot, in general, multiply two matrices that have the same shape. And you do not multiply a matrix coordinate-wise. So let A be an m by n matrix, and B an n by p matrix. So this has m rows and columns. This has n rows and columns. And if you want to multiply the matrices A, B, you can do it exactly when this is m by n, this is n by p. These two numbers are the same. The number of columns of the matrix on the left equals the number of columns of the matrix on the right. And let me start with a simple example. Suppose I take a 1 by n matrix. What's a 1 by n matrix? It's a matrix that has one row and n columns. It's a row, it's a n-dimensional, it's also what we would call a row vector. And suppose we take an n by 1 matrix, which is what we call a column vector. N rows, 1 column. So let's call this, let me just call this A, and call this B. I should call this A and B. How do we multiply them? You multiply them by multiplying the ith coordinates, I going from 1 up to n, and adding. So let me draw a better picture of this. Let me just write this as A1 up to AN, B1 up to BN. This is by definition, A1, B1 plus A2, B2, A3, B3 up to AN, BN. So that's how you multiply. This is 1 by n. This is n by 1. This is really a very important definition. So if you think of A as the vector A1, A2 up to AN, which is an n by 1 matrix, A transpose is A1, A2 up to AN. And here we're multiplying A transpose times B. This is sometimes called the inner product, dot product, or scalar product of the vectors A and B. And it's often denoted as A, B, in parentheses. In calculus, you would often write this as A dot B. This is as the dot product. So, but the point of this is, if you take two vectors of the same dimension, you can multiply them and get a scalar, you get a number. But it's based on this definition of, if you have a row vector and a column vector, this is the product. And we extend this to matrices as follows. So let me give you the general definition. And so suppose this is m by n, and this is n by p. So the first row of this matrix, this is A, this is B, A11, A12 up to A1n. This has n columns. A21, A22 up to A2n. The ith row is AI1, AI2 up to AIN. And the last row, AM1 up to AMN. So the important thing is this matrix A has n columns. So each row has n numbers in it. Now the matrix B has n rows. If you look at the first column, it's B11, B21, see BI1 down to BN1. The first column of B is also a vector with n entries. And the jth column would be B1J, B2J, down to BNJ. And they're P columns altogether. So the last column, the pth column, would be B1P, B2P, down to BNP. So the matrix A has m rows, each of which has n scalars. So each row is a n-dimensional row vector. The matrix B has p columns, and each column is an n-dimensional column vector. And if we're going to define A, B equals C, so this is m by n, this is n by p, and the matrix C is going to be like the n's cancel, it's going to be an m by p matrix. And in this matrix, if you take the ith row and the jth column, that's called the entry Cij. What is the ijth component of the product matrix? It's what you get by multiplying the ith row of A with the jth column of B. So Cij will be this times this, AI1 B1J plus AI2 B2J all the way up to AIN BNJ. So as I goes from 1 to M, there are M rows, and J goes from 1 to P, there are P columns, this is the definition of matrix multiplication. So let me write it down formally, and then I'll do some examples. And from the examples, you should get the idea of what is going on. So we have A is Aij, let's call it Aik. B is Bkj. So here, I goes from 1 to M, and K goes from 1 to N. This matrix has M rows and N columns. This matrix has N rows and P columns. And we're going to write C, the product of A and B, Cij. So this will be an M by P matrix. And the formula is that Cij, the ijth entry of the product, is the sum, K goes from 1 up to N, Aik Bkj. So this is the magic formula for matrix multiplication. If you have an M by N matrix and an N by P matrix, you can multiply them. What's important is, and what is essential is, that the number of columns of A equals the number of rows of B, and this is the formula. So let's look at some examples. Let's take 1, 2, 3, 4, 5. This has two columns, so this has to have 2 rows. Let's make it like this. So this is, actually, let me start with something. Just 1, 2, 3, 4 times 5, 6, 7, 8. So this is 2 by 2, this is 2 by 2. So the product is also going to be 2 by 2. And what is the number that is here in the first row, first column? You multiply the first row times the first column. 1 times 5 plus 2 times 7 is 5 plus 14. Second row, first column, you multiply the second row into the first column. 3 times 5 plus 4 times 7, 15 plus 28, I think it's 43. First row, second column, 1 times 6 plus 2 times 8, 6 plus 16 is 22. Second row, second column, 18 plus 32 is 50. So 1, 2, 3, 4 times 5, 6, 7, 8. The product is the matrix 19, 22, 43, 50. So if you look at the notes, the chapter on matrices, you'll see a lot of examples. Let me do one that's in the notes. This is on the bottom of page 8, the beginning of page 9. So suppose we have A is the matrix 2, minus 3, 1, 0. 5, 0, minus 4, 1. And B is the matrix 1, 2, 4, 0, minus 2, 7, 3, 1, 0, minus 1, 5, 3. So this is A, 2 rows, 4 columns, 2 by 4. This is B, 4 rows, 3 columns, 4 by 3. The product, C, will be 2 by 3. Okay, the 4's cancel in some sense, 2 by 3. And let's compute C. So C is going to have 2 rows, 3 columns. First row, first column entry. This is C11, C12, C13, C21, C22, C33. So C11 is the sum, K goes from 1 up to 3, A1K, BK1. A11, B11. This is A11, B11, plus A12, B21, plus A13, B31. This is A11, oops, sorry, up to 4, plus A14, B41. So I take 2 times 1, so I'm multiplying the first row times the first column. First row of A times the first column of B. I get 2 times 1, minus 3 times 0, 1 times 3, 0 times minus 1. That's 2 plus 3 is 5. For the first row, second column, I multiply the first row into the second column. 2 times 2 is 4, minus 3 minus 2 is 6, 4 plus 6 is 10, plus 1 plus 0, I get 11. First row, third column, I multiply the first row of A into the third column of B. I get 8 minus 21, 8 minus 21, minus 13, plus 0 plus 0, minus 13. And so on. This row into this, 5 minus 12 is minus 7, minus 1 is minus 8. Second row, second column, 10 minus 4 is 6, plus 5 is 11. Second row, third column, 20, 0, 0, 3, 23. So this is the product of those two matrices. And there are a number of examples in the text, and there are a number of homework problems, and you really need to do a lot of examples to make sure you're able to carry out matrix multiplication. And matrix multiplication satisfies certain very nice properties. Properties of matrix multiplication. The first is it's associative. So where the products are all defined, AB times C is A times BC. A, B, and C are matrices. You can multiply A and B, you can multiply A, B, and C. Wherever these matrix multiplications are defined, you have this associative property. It's also distributive. A times B plus C. B and C have to have the same shape. It's AB plus AC. And also, A plus B times C is AC plus BC. Third, there's the n by n identity matrix. That's a square matrix with ones down the diagonal and zeros everywhere else. And if A is an m by n matrix, you multiply A on the right by in, you get A. And if you multiply A on the left by in, you also get A. So this is a kind of identity element. It's analogous to the number 1 in arithmetic. Now, here is an extraordinarily important fact that distinguishes matrix multiplication from multiplying, for example, real numbers. Matrix multiplication is not commutative. What that means is that, in general, AB is not the same as BA. So let's look at an example. Let's see if I have one in the text. Yep. Here's a simple example. Suppose A is the matrix 0, 2, 3, 0, and B is the matrix 5, 0, 0, 7. So what is AB? 0, 2, 3, 0 times 5, 0, 0, 7. When I do my matrix multiplication, I get 0 plus 0, 0 plus 14, 15 plus 0. I get this matrix. When I multiply in the opposite order, 5, 0, 0, 7 times 0, 2, 3, 0, I get 0 plus 0, 10 plus 0, 0 plus 21, 0 plus 0. And if you look at these two matrices, they're different. Here there's a 14, here there's a 10, here there's a 15, here there's a 21. So AB is different from BA. Let's take two other matrices. Suppose I take A to be 5, 4, 4, 3, and B to be 11 minus 3 minus 7 minus 2. So let's look at the products. A times B, 5, 4, 4, 3, 11 minus 3 minus 7 minus 2. If I multiply these, I get 55 minus 28 is 27. Minus 15 minus 8 is minus 23. 44 minus 21 is 23. minus 12 minus 6 is minus 18. So this is A times B. If I multiply in the opposite order, B times A, 11 minus 3 minus 7 minus 2 times 5, 4, 4, 3, I get 55 minus 12 is 43. Already we see they're different. 44 minus 9 is 35. Minus 35 minus 8 is minus 43. Minus 28 minus 6 is minus 34. This is AB, this is BA. They're completely different matrices. Again, not equal. So this is really a fundamental fact about matrix multiplication. The order in which you multiply matrices, even when the order is when the products are defined, AB and BA are both defined, is not commutative. I mean, it might be that in some special cases, AB does equal BA, but in general, it's not true, so you cannot assume that it's true ever. If A and B are square matrices, n by n, number of rows equals the number of columns, AB and BA are both defined. And a square matrix A is said to be invertible if there exists a square matrix B, an n by n. There exists an n by n matrix B such that A times B and B times A are both equal to the n by n identity matrix. So for example, if A is 5, 3, 3, 2, this is a 2 by 2 matrix. And B, let's say B is 2 minus 3 minus 3, 5. Let's see if I made a lucky guess. What is A times B? 5, 3, 3, 2. 2 minus 3 minus 3, 5. This is 10 minus 9 is 1. Minus 15 plus 15 is 0. 6 minus 6 is 0. Minus 9 plus 10 is 1. This is the 2 by 2 identity. If I multiply in the opposite order, 2 minus 3 minus 3, 5, 5, 3, 3, 2. This is 10 minus 9 is 1. 6 minus 6, minus 15 plus 15, minus 9 plus 10 is 1. So A times B and B times A are both equal to the identity. So the matrix A is invertible, and because there exists a B such that AB equals BA is the identity. And there's a general problem. Given a matrix A, determine if it's invertible, and if it's invertible, find the corresponding matrix B. And some problems have many solutions. Some problems have only one solution. This is a problem that has only one solution. If A is invertible, and let's say A times B is the identity, and C times A is the identity, then B equals C. You can't have two different matrices that multiply by A on the right and the left and give you the identity. And the proof of this, let's see, proof. So the proof just uses the associativity of matrix multiplication. So C is C times the identity. So these are n by n matrices. Plus multiplying any matrix by the identity just gives you back the matrix. But the identity is A times B. And by associativity, C times AB is the same as CA times B. But CA is the identity. And the identity times B is B. So if AB is the identity and CA is the identity, B has to equal C. So the inverse of an invertible matrix, a matrix that has an inverse, is unique and denoted A inverse, A power minus 1. So for example, if we look at the matrix we just considered, 5, 3, 3, 2, then A inverse is 2 minus 3 minus 3, 5. And in general, it's important to know if a matrix has an inverse, and it's important to know how to compute the inverse. I should also add, if you can multiply matrices, if you have A, suppose A is an n by n matrix, then A times A, which we'll call A squared, is an n by n matrix. And A times A squared, which we'll call A cubed, is again an n by n matrix. So for any matrix A, if it's a square matrix, you can form the powers A squared, A cubed, and so forth. And you can prove that there is a power law. You have A to the K times A to the L. That's A to the K plus L. So this property that you see in algebra, X to the K times X to the L is X to the K plus L, also applies to square matrices. Let's look at a special case of matrix multiplication. Suppose you have an m by n matrix A, and we have an n by 1 matrix, which is a column vector, X. So A is m by n. X is a matrix. Every column vector is an n by 1 matrix. So n and n, they're the same. So this is, call this Y. This is going to be an m by 1 matrix, or an m-dimensional column vector. And let's look at an example. Suppose we have 1, 2, 3, 4, 5, 6. This is a matrix. 2 by 3. 7, 0, minus 2. this is 3 by 1, you're going to get a 2 by 1 or a two-dimensional column vector. When you do the matrix multiplication, you get 7 minus 6 is 1, 28 minus 12 is 16. This matrix times this vector is this vector. Suppose I take 1, 2, 3, 4, 5, 6 times the vector x, y, z. Or maybe I'll write it as x1, x2, x3. I get, again, I'm going to get a two-dimensional column vector. This is x1 plus 2x2 plus 3x3, 4x1 plus 5x2 plus 6x3. So if you multiply a matrix times a vector, you get another vector. And let's call this vector b1, b2. So this is the same as saying x1 plus 2x2 plus 3x3 equals b1, and 4x1 plus 5x2 plus 6x3 equals b2. And if you had started with this is two equations and three unknowns, you could rewrite this as a vector equation. If we let A be the matrix 1, 2, 3, 4, 5, 6, it's the matrix of coefficients of the equations. x1, x2, x3, those are the variables we're trying to solve for. And the right-hand sides of the equation, b1, b2, it's this. If we call this A, this is the vector x, and this is the vector b, this system of two equations and three variables is the same as the vector equation ax equal b. So to solve the system of two equations and three unknowns, it's the same as trying to solve a vector equation. Given the matrix A, and the vector B, find the vector x such that ax equals b. And this is a general fact that we can translate any system of linear equations into a vector equation or a vector matrix equation. So what is the general system of m equations in n unknowns? It's a11x1 plus a12x2 up to a1 n xn equals b1, a21x1 plus a22x2 plus a2n xn equals b2, down to a m1 x1 plus a m2 x2 plus a mn xn equals b sub m. This is m equations in n variables. So let A be the m by n matrix of coefficients of these equations. So A is the matrix. It's going to be m by n. In the first row, the n numbers are these coefficients. A11, A12, up to A1n. Second row with the coefficients of the second equation. A21, A22, up to A2n. Down to the mth row, you take the coefficients of the mth equation. So this is called the matrix of coefficients of the equation. This is an m by n matrix. Let B be an m-dimensional vector, which is the right-hand sides of these equations. And let x be the n-dimensional vector of the variables. So this system of equations, to find the solution for this system of equations, is exactly the same as finding a vector x such that the matrix A times x is B. So the matrix of coefficients of the equations, that's A, and AX equal B, is simply a matrix way to write down a system of linear equations. You can go back and forth between the matrix representation of the system and the sort of high school algebra representation of the system. I mean, in high school algebra, the basic problem is solving two equations and two unknowns, like 3x plus 5y equals 7, 2x minus y equals 8. Solve these equations. In matrix form, the matrix of coefficients would be 3, 5, 2 minus 1. The variable x would be xy. The right-hand side b would be 7, 8. So this system of equations is exactly the same as saying find a vector x, two-dimensional, such that ax equals b. It's exactly the same thing. Now, in chapter 1, we solved a system of equations by Gaussian elimination. And I'm going to show you now how to do Gaussian elimination using a matrix, which is a little bit computationally more efficient. So for that, we use the augmented matrix. So here we had a system of equations, m equations and n unknowns. This was the matrix A, and this was the vector B. So corresponding to this system of equations, we write what is called the augmented matrix. The matrix of coefficients had m rows and n columns. And in the augmented matrix, we're going to add one column. So instead of m by n, it'll be an m by n plus 1 matrix. Now the column we add is the b's that are on the right-hand side. So the augmented matrix corresponding to the system will have A11, A12 up to A1n, AM1, AM2, AMN. This was the matrix of coefficients, and we augmented by adding one more column, B1, B2, down to B sub n. So this is the augmented matrix corresponding to the system of equations. So if we have, for example, x plus 2y equals 5, and 3x plus 4y equals 6, the augmented matrix, well, the matrix of coefficients is 1, 2, 3, 4, and we augmented with this additional column 5, 6. So that's the augmented matrix for this system of equations. And if we let okay, now I want to use the augmented matrix and Gaussian elimination to solve a system of equations. So let me just recall what we do in Gaussian elimination. In Gaussian elimination, you go from one system of equations to an equivalent system. An equivalent means the equations have the same solutions. And what you were allowed to do was to interchange two equations. So let's see, let me just write this down. So in Gaussian elimination, you can do three things to a system of equations. You can interchange two equations. You can multiply an equation by a non-zero scalar, or you can add a multiple of one equation to another equation. Now, what does this mean if you're looking at your system of equations and converting it into matrix form? So if you have your equations, a11 x1, a1n xn equals b1, a21 x1 up to a2n xn equals b2, and so forth down to am1 x1 plus up to amn xn equals b sub m. If you had your augmented matrix, a11, a12, a1n, b1, a21, a22, a2, and b2, and so forth, am1, amn, bm. What does it mean to interchange two equations? It's the same as interchanging two rows of the augmented matrix. What does it mean to multiply an equation by a non-zero scalar? Multiply a row by a non-zero scalar. What does it mean to add a multiple of one equation to another equation? It means add a multiple. I don't have to write it down because it's all written down in the notes. You can add a multiple of one row to another row. And each of these operations on equations or on the rows of a matrix can be inverted. And if you apply elementary operations to the equations, it's the same as applying that same sequence of elementary operations to the rows of an augmented matrix. And every time you do something to the augmented matrix, you can translate that back into a system of equations. And the systems of equations are always equivalent. They have the same solutions. And what you want to do in Gaussian elimination is to find an equivalent system of equations where each equation starts with a variable x1, x2, and so forth. Wherever that you have, and that initial variable will have a coefficient of 1. And wherever that variable occurs in an equation with coefficient 1, in every other equation, it's not there, it disappears. That's coefficient 0. And these first non-zero coefficients move to the right as you go from one row to the next. And the bottom rows are all 0. So let's just do this for some examples. And that really is, I think, the only way to understand what's going on. So suppose we have the system of equations 9x plus 11y equals -1, and 5x plus 6y equals 3. So we have two equations and two unknowns. The augmented matrix will be 9, 11, -1, 5, 6, 3. Now, when we're trying to solve these equations by Gaussian elimination, the first step might have been to divide the first equation by 9. So you get a coefficient of 1. So you get x plus 11 over 9y equals -1 over 9. 5x plus 6y equals 3. And the corresponding operation on the matrix would be to divide the first row by 9. You would get 1, 11 over 9 minus 1 over 9, 5, 6, 3. The next thing you would do with the equations is eliminate the x from the second equation by subtracting 5 times the first equation. So the first equation is still unchanged. It's this. If you take the second equation minus 5 times the first, 5x minus 5x is 0 times x. 6 minus 5, say 54 over 9. 6 minus 55 over 9. 6 is 54 over 9, so this is 54 minus 55 over 9 is -1/9 y. 3 minus 5/9 is 3 plus 5/9 is 32 over 9. Here, if you take the first equation, that doesn't change, and you subtract 5 times, the first row, you subtract 5 times the first row from the second row, 5 minus 5 is 0, 6 minus 55 over 9 is -1 over 9, 3 plus 5 over 9 is 32 over 9. Well, notice in each case, this matrix is the augmented matrix for this system. The next thing we would do here to get we want this to have a coefficient of 1. Multiply this by -9, you get y equals -32. Here you multiply the second row by -9, you get 0, 1, -32. Then you want to eliminate this or this. So you have y equals -32. You take the first equation minus 11/9 times the second, you get x plus 0 equals, let's see, -1/9 minus -1/9 minus, I'm adding -11/9 times the second equation to the first. So that's -11/9 times -32. So 11 times 32 is 352 plus 1 is 353. Is that right? Sorry, this is plus. This is 3 is -1/9 plus 352 over 9, which is 351 over 9, which is 39. And here, if I take the second row of the matrix, multiply it by -11 over 9 and add to the first row, I get 1, 0, 39. So it's exactly the same sequence of operations. It's somewhat more convenient to use the matrix. And we want to put the matrix into a form where in each row, the first non-zero entry is a 1. And as you go from one row to the next non-zero row, the first non-zero entry, the 1, is to the right of where it was in the previous row. And where you have this initial 1, everything else above and below it is 0. And any rows that are all 0 are at the bottom of the matrix. So a matrix in that form is said to be in row reduced echelon form. So let's see. So a non-zero means at least one coordinate of the matrix is different from 0. A non-zero m by n matrix A, coordinates aij, is in row echelon form if it has the following properties. If there are positive integers k1 less than k2 less than k3, strictly increasing case of R, with the following properties. So we're looking at our matrix, and we have the first R rows, but altogether they're M rows. So for I going from 1 up to R, the entry AI k sub I. So we have k1, k2 up to k sub R. These are increasing numbers. So A1, K1. In the first row in the K first column, you have an entry which is non-zero. Actually, I'm just going to make this define row reduced row echelon form. AI, Ki is equal to 1 for I going from 1 up to R. That's the first property. Second, if you look at in row I, Aij is 0 for j less than k sub I. So in each row, you have zeros, and then the first non-zero entry that occurs is a 1. And because the k's are increasing, these 1s are moving to the right as you go from one row to the next. And for I going from R plus 1 up to M, and all the bottom rows, these are all zeros. So all your 0 rows at the bottom, and in the non-zero rows, as you go from left to right, the first non-zero number you see is a 1. And these 1s are moving to the right as you go from one row down. And above and below that 1, they're all zeros. So A sub I, A sub L, K sub I is 0 for L different from I. So in the ith row, you have a 1 in the K sub ith place, and everything above and below that is 0. That's what it means to be in reduced row echelon form. And Gaussian elimination is the process of putting a matrix in reduced row echelon form through these elementary row operations of a matrix. The elementary row operations are interchanging rows, multiplying a row by a non-zero scalar, and adding a multiple of one row to another. And when you do this, you will end up with the matrix. You convert this matrix back to the system of equations, and you found the solution to the system. So this sounds, I think, rather complicated. And the only way to understand it is to work through examples. So the theorem says that every n by n matrix is equivalent to a unique reduced row echelon matrix. Equivalent means by these elementary row operations. So let's look at an example. And this is an example in the text on page 35. I have a 3 by 3 matrix, 3, 13, 37, 1, 4, 13, 2, 14, 14. And I want to put this in reduced row echelon form. So I want the first non-zero entry in the first row to be a 1. I could divide the first row by 3 and get fractions. It's easier if I just interchange the first two rows. 1, 4, 13, 3, 13, 37, 2, 14, 14. So here what I did was interchange rows 1 and 2. Okay, so now I have a 1 in the first row, first column. I want zeros underneath it. To get a 0 here, I'm not changing the first or the third rows yet. To get a 0 here, I add -3 times row 1 to row 2. Or same thing. I subtract 3 times the first row from the second row. So 3 minus 3 is 0. 13 minus 12 is 1. 37 minus 39 is -2. So I subtracted 3 times the first row from the second row. Then I want to get a 0 here. So I have 1, 4, 13, 0, 1, -2. I can get a 0 here by subtracting 2 times the first row from the third row. 2 minus 2 is 0. 14 minus 8 is 6. 14 minus 26 is -12. So my first column is good. It starts with the 1, everything else is 0. Then I look at the second row. I want to have a 1 here, and actually I already do, so great. But then I want to get a 0 here and a 0 here. So here's the second row and the third row at the moment. To get a 0 here, I take the first row minus 4 times the second row. 1 minus 0 is 1. 4 minus 4 is 0. See, -4 times -2 is 8. 13 plus 8 is 21. Then I want to get a 0 here. 1, 0, 21. 0, 1, -2. If I subtract 6 times the second row from the third row, I get all zeros. It's pretty good. And now this matrix is in reduced row echelon form. In each row, the first non-zero entry is a 1. Any zero row is at the bottom of the matrix. Wherever there's an initial 1, above and below is just 0. And as you go from the first to the second row, the 1 is moved to the right. Now, this initial matrix can be looked at as the augmented matrix for the system of equations 3x plus 13y equals 37, x plus 4y equals 13, 2x plus 14y equal 14. If I started with this system of equations, this would be the augmented matrix. This matrix is the augmented matrix for a different system of equations. X equal 21, y equal minus 2. That means this is the solution for this system. We solve this system of equations by taking the augmented matrix and putting it in reduced row echelon form. Let's just check that this really is the solution. 3x plus 13y is 3 times 21 plus 13 times minus 2 is 63 minus 26 is 37. That checks. X plus 4y, 21 plus 4 times minus 2 is 21 minus 8 is 13. That checks. 2x plus 14y is 42 minus 28 is 14. That checks. So this really is the solution of these equations. All right. So that is today's lesson. But we covered a lot. So what we covered today is pages 1 to 36 in chapter 2 on matrices. And I'll spend a lot of time tomorrow doing more examples. But you should take advantage of the overnight to solve problems using reduced row echelon matrices, and maybe even try to solve some problems this afternoon. And I have a help session at 7 p.m. And I encourage you to have to log on and ask questions if you have difficulty learning this technique. But this is a basic technique in linear algebra. You start with a system of m equations and n unknowns. You write down the augmented matrix. You use elementary row operations to put the system of equations to put the augmented matrix into reduced row echelon form. When you take that and write that as a system of equations equivalent to the original one, you will have a solution, or you will learn that there is no solution. What would it mean to have no solution? Well, suppose you had an equation that looks something like 0, 0, 1, 0. You write this as an equation. This is x1, x2, x3. This would mean, 0, 0, 0, 1. This would be the equation 0 equals 1. There is no such equation. You end up, if you have an equation with all zeros and a 1 in the last column, that's impossible. 0 doesn't equal 1. So that would mean that the system that you started with is inconsistent. It has no solution. So this reduced row echelon form not only finds all solutions of systems that have solutions, of consistent systems, but it also shows, it also tells you if the system is inconsistent and has no solution. Okay. Okay, we've done a lot. Well, we did a week's work today. And it takes a week to learn this, but in the summer, you don't have a week. You really have very little time. And you really need to learn this technique. Okay. I'm available as always tonight at 7. If you have questions, I encourage you to log in. Oh.
Yeah, I only got one, professor. It's about the homework.
I'm sorry. I can't understand. Can you repeat what you're saying, please?
Yes. It's about the homework. Last night I was trying to finish my homework, but I was looking at section 1, and I couldn't. Well, chapter 1, I couldn't find the homework on the textbook. I don't know if I
So the
couldn't
textbook,
identify it or
the textbook is not the book that I posted on under course materials. There's a whole book I posted. It's an example of one of many books that are on linear algebra that are available for free. And I encourage students to look at alternate presentations of the material. But the textbook, the text that we are using are the individual chapters that I upload to course materials. There's chapter 1, linear equations, chapter 2, matrices. That is the text. The other book is just there to study if you want some additional presentation of the material.
Okay, so you're not taking, you're not putting the homework from the textbook that is called Understanding Linear Algebra?
No. That's just there as an additional resource. It's not the textbook for this course.
Okay. So I'm gonna be doing the homework 1 tonight. I know it's gonna be late, but I'll do it tonight. And
it's okay. If you turn it in late, that's fine. In the summer, where it's very intense, it's perfectly okay to turn your homework in late. It's just bad if you fall behind too much.
Okay. Thank you very much, Professor.
Okay.
Well, have a great day, Prof.
Thank you.